So now we'll talk about modular arithmetic. Many applications can be found related to this in computer science, especially in cryptography. Um, a very basic example that we can face daily is this. Suppose that we have the 12 hours on a standard US clock. So if the time is 11 hours, after 3 hours, it's going to be 11 plus 3, but we don't say it's 14. Okay, we say it's 2 o'clock. Why? Because at 12, after 12, then we start again. So like, for example, 12 plus 1 is 1. It's not 13. So 1 hour after 12 is 1. Okay, so using this idea, this is what we call modular arithmetic. So this is like you are working in this modulo 12. Okay, so the highest number is 12. You go from 1 to 12 and then you go back. So for example, if I want to do 10 plus 5, I don't write 15. So it's like if it's 10 a.m. now and I have 5 hours after 10, I don't say 10 plus 5 is 15. Well, I say that 10 plus 5 is 3. Okay, so this idea is what we call modular arithmetic. So let's start here with some definitions. If a and b are integers, and integers can be both positive, can be negative, doesn't matter, but here I want m to be a positive integer. Okay, then I say that a is congruent to b modulo m if m divides the difference of these two numbers, if m divides a minus b. Okay, for example, I can say that 17 is congruent to 12 modulo, I write this, to 12 modulo, well, I didn't introduce this yet, to 12 mod m, mod 5. Okay, so what does this mean? This means that 17 is congruent to 12 mod 5. Well, why 17 is congruent to 12 mod 5? Because look, 5, which is m here, because m divides a minus b. So this is like a, this is like b, and this is like m. So m, which is 5, divides a minus b, 17 minus 12. Well, 17 minus 12 is 5. I know that 5 divides 5, so that's fine. Okay, so we use the following notation that I just introduced in the previous example to say that a is congruent to b mod m. So a congruent to b mod m, it does not mean that a is equal to b, but it means, as we will prove later, that if I divide a by m and if I divide b by m, I get the same remainder. Okay, it also means that m divides the difference between a and b. It doesn't matter if you do a minus b or b minus a. If a is not congruent to b mod m, then we simply just use the following notation to indicate that a is not congruent to b mod m. For example, 7 is not congruent to 12 mod 4. Why? Because if I take the difference, I have to ask myself the following question. Does 4 divide 7 minus 12? No, because 7 minus 12 is negative 5. 4 does not divide minus 5. And you can say 12 minus 7. 4 does not divide 5 as well. So it doesn't matter in this case whether it's positive or negative. Okay, so here 17 is congruent to 5 mod 12. Why? Because 12 divides 17 minus 5. Because 17 minus 5 is 12, so this is right. Okay, so I can write 17 is congruent to 5 modulo 12. Also, 38 is congruent to 3 modulo 7 because simply if you take the difference between the two numbers a and b, you get 35, and 35 is divisible by 7, or 7 divides 35. So this is true as well. 3 is congruent to 38 as well. So I want you to see here that it doesn't matter if you write, I mean, it's like the equality. It doesn't matter if you say a equal b or b equal a. Here it's the same. It doesn't matter if you say a is congruent to b modulo m or b is congruent to b modulo or b is congruent to a modulo m. So switching the order doesn't matter here. -3 is congruent to 4 mod 7. So also you can have like a negative number is congruent to a positive number. That's fine because it will satisfy the definition. As long as it satisfies the definition, then we're fine. Look at this here. This is A, this is B. Take A minus B, so that's going to be -3 minus 4, which is -7. Is -7 divisible by 7? Sure, because -7 is equal to 7 multiplied by -1. -3 is not congruent to 3 modulo 7. And the reason is shown here because if you take the difference, -3 minus 3 is -6, and -6 is not divisible by 7. Okay, another example, -29 is congruent to -13 modulo 8. Theorem: let A and B be integers, and let M be a positive integer. Then A is congruent to B modulo M if and only if A mod M is equal to B mod M. Well, first let's see what we are trying to do in this theorem. I have two directions to prove. Okay, the first direction, I have A congruent to B mod M. So let's write what does it mean to say that A is congruent to B modulo M. A is congruent to B modulo M means that to B mod M, then there exists, then M divides A minus B. Okay. That means there exists an integer k in Z such that A minus B is equal to k multiplied by M. Okay, and M is a positive integer. Okay, so this means that A is equal to B plus k times M. Okay. So I have all these things. Fine. Now I want to show that A mod M is equal to B mod M, and I mean any of these can be useful to me. So that means I want to show that A mod M equal B mod M, meaning that I want to show that if I divide A by M and if I divide B by M, I should get the same remainder. Okay, so by the division algorithm, when I divide A by M, okay, so when I divide A by M, this means that A is equal to M times, let's say, Q1 plus R1. And what's R1? Well, R1 is between 0 and M. Okay, this is by the division algorithm. And Q1 and R1 are unique. And when I divide B by M, this means that B is equal to M multiplied by some quotient plus some remainder R2. Again here, I have this restriction. Okay, so that R2 is between 0 and M. Now, I know that M divides A minus B. Or I know that A is equal to B plus KM. I can use any of these two. Okay. So let's look at M divides A minus B. So A minus B equal K times M. So I have A minus B equal K times M. That means the following. Instead of A and instead of B, I'm going to put the following equation. So that's going to mean MQ1 plus R1 minus MQ2 minus R2 is equal to K times M. So this means the following, that M times Q1 minus Q2 plus R1 minus R2 is equal to K times M. Move this to the other side. So this means that R1 minus R2 is equal to m multiplied by k minus q1 plus q2. Just do the algebra here and you will see this. Okay, this means something very important. This means that m divides r1 minus r2. Okay? Because I'm saying here that r1 minus r2 is equal to m times some integer z. So by the definition of divisibility, this means that m divides r1 minus r2. Okay, but here I have a problem. r1 is less than m, r2 is less than m, and both of them are between 0 and m. If I take the difference, that's not going to be bigger than m. So which number m can divide? So that number is smaller than m. Well, the only possibility in this case would be 0. Okay, any number divides 0. So then r1 minus r2 must be equal to 0, which means r1 has to equal r2. Oh, what was r1 and r2? Remember, r1 was the remainder of dividing a by m. So this is r1, which is a mod m. And r2 is the remainder of dividing b by m. So this is r2. So I got r1 equal r2, which means I got a mod m equal b mod m. Okay. Now the other direction, it's much easier. So we leave it as an exercise. It's just to start from a mod m equal b mod m. Write what this means. You can go backwards. You can follow this proof and go backwards to show that m divides a minus b. So it's easier than this. So you should try it. So here's a theorem. Look, so far we had the following definition and a theorem. The first definition says this, that a congruent to b mod m. That's the first definition we gave. This is equivalent to say that m divides a minus b. That's the basic definition. Then we added to this the previous theorem, which says that a congruent to b mod m is equivalent to say that a mod m is equal to b mod m. Okay, meaning that if I divide a by m, b by m, I get the same remainder. And now this is another theorem actually. Okay, and in practice, if you want to prove something related to congruence, you can use any of these three definitions. Okay, so you can use the first, the second, or this theorem. This theorem is really nice and I like it, and it's easy. It's more handy in proofs. Let a and b be integers and positive, then a congruent to b mod m if and only if there is an integer k such that a equal b plus km. The proof is very simple because I start from here, a congruent to b mod m. By the original definition, this means this is equivalent actually to m divides a minus b. So this is equivalent to this statement. There exists k in z such that a minus b equal km. Now just move b to the other side. So this is equivalent to say that there exists k in z such that a equal b plus km. And this is the proof here. So I proved each step using equivalency so that no need to do two directions. So then from now on, we can add this to the list. A congruent to b mod m. This simply means also that there exists k in z such that a equal b plus k multiplied by m. So modular computation. Now we'll talk a little bit more about modular computation when we have numbers, not just theory. So when performing arithmetic operations, we care only about the congruence class of the result modulo n. So we may at any time replace a number by a more convenient representative of its congruence class. So here's an example. Suppose that my goal is to find 79, okay, times 23 modulo 5. Okay. Or I want to see like 79 times 23 is congruent to what modulo 5? It's the same idea actually, because we showed previously that A congruent to B mod 5 means that A mod 5 is the same as B mod 5. So what I can do is the following. I don't need to, I can do this. I can do, well, this is equivalent to find, so this is equivalent to find 79 times 23 mod 5, if you want. Okay, so the answer that you get here, you may put it here. But here's a simpler way. No need to do 79 times 23. You get a big number, then you have to divide it by 5, and then you have to find the quotient and remainder. One thing we can do easily is the following. I know that I can divide 79 by 5, okay, and the remainder is going to be 4. Okay, because 75 is divisible by 5, so what's left is 4. And I know that if I divide 23 by 5, that's going to be 4, and the remainder is going to be 3 as well. Okay, so 23 is going to give me 3, 79 is going to give me 4. So instead of doing 79 times 23, I will be doing 4 times 3. Okay, 4 times 3 is 12, and 12 is 2. So I can keep reducing modulo 5 in this way. Okay, so I can reduce the product before multiplying till I get nice number. Like 12 is a nice number here, it's small number. When I divide 12 by 5, my remainder is 2. So that's 12 is mod 5 is congruent to 2 mod 5, or 12 is congruent to 2 mod 5, because we are using the following idea, that 12 congruent to 2 mod 5 by the previous theorem. This is equivalent to say that 12 modulo 5 is equal to 2 modulo 5. Okay, that's the theorem we proved earlier. Okay, and now you can verify when you divide 12 by 5. Okay, so 12, this is equal to 5 times 2 plus 2, 10 plus 2. So that's my remainder. And for 2 mod 5, so 2 equal 5 times 0 plus 2. So 2 is my remainder as well. So they do have the same remainder. Okay. And again, by the definition, if you take the difference between them, it's divisible by 5 as well. So there's a strong connection between the congruence and between the modulo that we defined earlier at the beginning for the division algorithm, which represents just the remainder of the division. So here's an exercise, and I can show you how we can do this in multiple ways. Determine whether 17 is congruent to 34 mod 20. So I want to show if this is true. 17 congruent to 34 modulo 20. So I want to see if this is true. One thing I can do is the following. First, this is equivalent to say, to answer the following question. The first definition, you take the difference, 17 minus 34 equal minus 17. Is minus 17 divisible by 4? Divisible by 20? Well, the answer is clearly no. I mean, you cannot divide negative 17 by 20. So then I can conclude that that 17 is not congruent to 34 modulo 20. Another way to do this is the following. You find 17 mod 20, and then you find 34 mod 20, and then you compare the answers. If you get the same answers, then they will be congruent. But if you don't get the same answers, and that's what I expect now, then they will not be congruent, modulo 20. Now 17 modulo 20 is 17. Again, look, every time you have a positive number modulo a number that's bigger than that number, then the answer is 17. And the proof is very simple, because when you divide 17 by 20, you get quotient 0 and the remainder 20. So that's why 17 modulo 20 is 17. Now for 34 modulo 20, this is actually 14, because 34 is equal to 20 times 1. There's only 120 in the 34 plus 14. So clearly here, 17 mod 20 is not equal to 34 mod 20. As a result, 17 is not congruent to 34 mod 20. Now here we have, as I listed, some properties related to divisibility. Then here we do have some properties related to congruence properties. So first we're saying that A is congruent to A mod n. This should be obvious because due to the definition that A mod n is the same as A mod n. So if you divide A by n, it's going to be the same remainder, so that would be fine. Also, you can go with the regular definition. N divides A minus A. Yes, n divides 0. N divides 0. Any non-zero number divides 0. Okay, so that's a rule that you can always take. The reason is kind of simple because n, if you divide 0 by n, so 0 equal n times, you put the quotient to be 0 and you put the remainder to be 0 as well. Okay, so any non-zero number divides 0. So this should be fine. Now, if A is congruent to B mod n, then B is congruent to A mod n as well. Again, here the proof is easy. You can use different types of proofs. Here's an easy one. A congruent to B mod n. This means the following, that A mod n is equal to B mod n. Note something, that over here I'm using congruence. Over here I'm using the regular equality. Now, because I know in the regular equality that the left equals the right is the same as saying the right equals the left. So this is equivalent to say that m modulo n is equal to A modulo n. So this is equivalent to say that B is congruent to A modulo n. Okay. Another proof, if you want, A congruent to B mod n. This is equivalent to the following. There exists K in Z such that A equal B plus Km. Well, let's move this to the other side. So this is equivalent to say that B equal A minus Km, which means that B equal A plus negative K multiplied by M. So here this is equivalent to say that B is congruent to A mod M. Why? Because B congruent to A mod M means B equal to A plus some integer times M. That's my integer, negative K. We didn't say that this K has to be positive, we just say it's an integer. So if K is an integer, certainly negative K is also an integer. If A is congruent to B mod n and B is congruent to C mod n, then A is congruent to C mod n. This is called the transitive property. Again, for this, you can use any of the definitions we gave. This means that there exists K1 in Z such that A equal B plus K1 multiplied by n. This means there exists K2 in Z such that B equal C plus K2n. Okay, now I want to show that A is congruent to C mod M. Actually, that should be n. It's a typo here. That should be n. Okay, so I want to show that A is congruent to C mod n. So what I need to do here is to relate A and C. Well, why don't we replace B by this quantity? So A is equal, instead of writing B, I write C plus K2n, and I got the K1n here. So I replaced B by C plus K2n. That means that A is equal to C plus K1 plus K2n. And I know that this is an integer. You can call it K. So this is A equals C plus Kn. And that's equivalent to what I need to prove, that A is congruent to C mod n. Okay. It can also be done maybe a bit easier if you just use the fact that A congruent to B mod n means A mod n is equal to B mod n, and you know that B mod n is equal to C mod n. By the transitivity of the equality, that's going to be valid as well. But I like to show this because this is kind of similar. I mean, the technique here is similar to the problems that we used to prove related to even and odd. Like you try to write it in a specific form using these integers. Okay, some more properties related to congruence, and this is related most to the um, congruence arithmetic. Like, if you know that A is congruent to B mod M and C is congruent to D mod N, here you have to be careful. I'm always working in the same modulo class. Always mod N. I cannot, like, if A is congruent to B mod N and C is congruent to B mod M, let's say, I can't do any kind of arithmetic between them. Okay. So if A is congruent to B mod N, C congruent to D mod N, then their sum or the difference are congruent as well. Okay. Hey, let's try to prove one of them. When I say A congruent to B mod N, then I will use the following definition. There exists K1 in Z such that A equal B plus K1N. And when I see C congruent to D mod N, then there exists K2 in Z such that C equal D plus K2N. Okay. Now let's take the sum of these two equations. This leads to A plus C equal B plus D plus K1 plus K2 multiplied by N. Okay, so that means A plus C is B plus D plus some integer K multiplied by N. This is exactly what A plus C congruent to B plus D means. Of course, modulo N. Now, the same proof will be done if you take the difference between these two functions. So instead of this plus, if you take the difference, you can prove the case where A minus C is congruent to B minus C mod N. Here's a similar one. AC is congruent to BD mod N. Again, we have A equal B plus K1M. I'm referring to the same setup from the previous proof. I have C equal D plus K2N. Sorry, N here. I should use N, not M. Now I want to show that AC equal BD. So in this case, I will multiply. So A times C, substitute A by B plus K1N, substitute C by D plus K2N. Then this means the following, that AC equal B times D plus B K2N plus D K1N plus K1 K2N square. Look, my goal is this. My goal is to show that AC is congruent to BD mod N. So I want to show that AC, so what I need to show is this, AC equal BD plus some constant K times N. Well, if you look at all these, I can factor out an N. So AC is equal to BD plus N multiplied by some integers like BK2 plus DK1 plus K1 K2 N. It's a sum of product of integers, so certainly it's an integer. So as a result, I have AC congruent to BD mod N. Here's another one. This is very similar to the one above, so you may try this as an exercise. Okay. It's not too bad. Now we'll do some examples just to show you how we can deal with this type of problems. Okay. So suppose that A and B are integers, And suppose that A is congruent to 4 mod 13, B is congruent to 9 mod 13. I want to find an integer C so that C is between 0 and 12 such that C is congruent to 9A mod 13. So here's what I do in this case. I'm working in mod 13 and I know that in mod 13 A is congruent to 4 mod 13. So I can start by saying that C is congruent to 9. Instead of A, I can put 4 mod 13. So this means that C is congruent to 36 mod 13. Okay, now here's the thing. I want to find C so that C is between 0 and 12. And I want to make sure that this is gonna make my congruence correct. Actually, there's more than one technique that I use to find C. Here's one technique. So first method, I can do the following. I can say that C mod 13, because I want C to be congruent to 36 mod 13, so I want C mod 13 to be equal to 36 mod 13. This is the theorem that we proved. I mean, these two things are the same. Okay, these two are equivalent by a theorem we proved. So basically, I want C mod 13. So I want a number C. When I divide it by 13, I get, okay, I know 36 mod 13. I know that if I divide 36 by 13, my quotient is 2 and my remainder is 10. Okay, so if I have 36, 13, 2 times 13, 26, subtract, you get 10, and then you stop here. So this is equal to 10. Okay, so I want a number C between 0 and 12, and when I divide this number by 13, I get 10. The only possibility is 10. So here you choose C equal 10. Okay? Because 10 mod 13 is 10, and now that would be satisfied. Okay, you can check it. If you do 10 is congruent to 9 times 4 mod 13, that's gonna be the same. And you can always verify by checking that 13 divides C minus 9A. Okay, so does 13 divides what is C? 10 minus 9 times 4. Well, 10 minus 9 times 4 is actually negative 26, and 13 divides negative 26 because negative 26 divided by 13 is negative 2. This is my first method. My second method is a bit different. Well, I start from here. I want to find C congruent to 36 mod 13. Now, when I work in mod 13, what's 13 mod 13? Well, remember this. 13 mod 13 is equal to 0. Because when you divide 13 by 13, the quotient is 1, the remainder is equal to 0. So, this suggests the following. You know, I can add zeros as much as I want. I can subtract zeros as much as I want. So then C is congruent to 36 minus 13 mod 13. That's not going to affect my answer because what I really did is I subtracted 0. So that means that C is congruent to, what is this? 36 minus 13 is 23 mod 13. Okay, well, I can choose C equal 23, but this is not in my domain because in the domain that they want for C is to be between 0 and 12. So subtract another 0. 23 minus, what's the 0 here, which is 13? Another 13 mod 13. So this gives me that C is congruent to 10 mod 13. Well, now I can choose C to be 10 and having C in my given range. Okay, so maybe someone will ask you, you know, well, I want C to be between minus 12 and 0. So in this case, you keep subtracting 13s. So I like to use this idea. I can subtract, I can add as much as I want multiples of 13, because basically what I'm doing here is I'm just adding or subtracting zeros. Okay. So this is the solution. Here's another example. Let's just try it. Find the integer c between 0 and 12 such that c is congruent to a plus b mod 13. So again here I start by saying this. That means that c is congruent. I replace a by 4, b by 9. Mod 13. So that means that c is congruent to 13 mod 13. Okay, now you see that I can choose c to be 13 in general, but again, I want my c to be between 0 and 12. So I subtract a 0. I'm using my method 2 that I showed you in the previous slide. So that means c is congruent to 0 mod 13. So then I can choose c to be 0. So choose c to be 0. This is going to make it. Okay. Let's say that I'm under the same question. Okay. But suppose that I'm changing c, okay, to be between let's say this is 13, negative 26 and negative 14. Okay, I can do that. So what's going to happen is that thing. So I'm going to start from here. C is congruent to 4 plus 9 mod 13. So this means that C is congruent to 13 mod 13. And then I will subtract 13s or multiple of 13s. Now you don't really have, I mean, you can have the calculator next to you. You don't really have to do 13 minus 13 minus 13 minus 13. You can do like 13 minus 2 times 13 and so on. So here I'm going to do this. This is equivalent to 13 minus 2 times 13, because I know that 13 minus 13 doesn't work. Okay, so this is what? Mod 13. So C is congruent to actually negative 13 mod 13. Well, unfortunately, if I choose C to be a negative 13, that's not in this range. So maybe I will need to subtract one additional 13. So C is congruent to negative 13 minus one additional 13 mod 13. So C is congruent to negative 26 mod 13. Well, negative 26 can be chosen here because it's in this interval, so I choose C to be minus 26. So it's very important to see how this works, and it depends really on the given value or the given domain of C. So this is the one that we just did, and then we made a variation for that one. That's the same, I mean, very similar question you should be able to try, and here's its solution. So you can try it by the method that you prefer. Okay. So here also I'm doing it in a different way. So actually using method 1. So once I end up with C congruent to this, then I was doing minus 665 mod 13, as you can see in the bottom. And I found this, and that's equal to 11. If you want to use method 2, what you're going to do here is negative 665. You will be adding, because that's a negative number and you want to make C between 0 and 12. You can keep adding multiples of 13 till you get a number between 0 and 12. Here you have to be very careful. Since we talked about the congruence properties, we have to mention something very important, that if A is congruent to B mod n, we mentioned the following property, that A congruent to B mod n, okay, then if P is not equal to 0, then AP is congruent to BP mod n. Okay, but here, so A times C is congruent to B times C mod n, as long as C is not 0. over here we have to be very careful. You cannot divide. So this is a very important remark. If A is congruent to B mod n, you cannot divide. Not only because when you do A over C, you may get fractions. No, you may have some numbers so that you can divide and you don't get fraction. Look at the example I have here. 18 is congruent to 42 mod 8. You can verify this. But if you divide by 6, well, 18 divided by 6 is what? That's 3. 42 divided by 6 is 7. Notice that 3 is not congruent to 7 mod 6. Mod 6. Okay, so we have to be very careful. Division is not allowed in general. There are some cases where we can divide. We can talk about these later after we talk about GCD and prime numbers. So we finish this by the following proposition. Suppose that A is congruent to 0 modulo M, then this implies that M divides A, and vice versa. If M divides A, then A is congruent to 0 mod M. The proof is actually simple. Let's look at this. A is congruent to 0 mod M. You can use any of the definition that you wish for this. That means that M divides A minus 0. That's the basic definition, or the first definition we have for the congruence, which means M divides A. Done. And also for the other direction, when you say M divides A, okay, that means A mod M is equal to 0. So that means that A mod M, if you want, is equal to 0 mod M, because 0 mod M is going to be 0. If you divide 0 by M, well, the remainder is going to be 0 as well. So then A is congruent to 0 mod M. Okay. So this is a really nice relationship between the congruence and the divisibility.